Today we are going to start with threads, and thread is everywhere. So basically, each and every operating system you are using, your mobile devices you are using, all are multi-threaded. Thread is basically created by a process for functioning efficiently, and because this is thread is more like splitting your task into smaller chunks, and then those chunks would be running on your system, whether it is a single core or a multi-core environment. Threads are more suitable for multi-core hardware because we have more cores and they can actually run on independently on different cores. So that is the whole concept of threads. Basically, why we need threads is because now we have multi-core system, and threads could be running independent to each other on different available cores, and that brings us with the parallelism. The parallelism could be created on a multi-core environment, but if you have single core system, then it means that it would be running just as a normal processes, because one process currently would be running on single core. So this is basically threads are uh, run within the application. So application or a process, it basically one process creates multiple threads. It could be 2, 3, and so on. We would try to see through your Ubuntu machine that if there are how many threads are running for each and every process. Multiple tasks within application can be implemented. Let us suppose if you are running a word processor, just your MS Office, then you can actually start a individual thread for one, which is basically updating the screen, second, which is fetching the information from the user, third, which is checking the spelling, and fourth thread could be your which answers the network request. So it is up to the program developer how many threads he or she wants to create for running an application for efficient utilization, because the threads would be utilizing the section or the memory of the process. So the resources which are allocated to one process would be shared by threads only. So it's not going outside the process. So just using the resources those are allocated for that particular process. And those are also called, threads are also called lightweight processes. So you can see LWP is a name that is usually used for threads. It basically increases the efficiency, and also the code simplifies the code, and kernels are generally multi-threaded. So Linux, Windows, everything is whatever operating system you see or you work on, they are multi-threaded operating system, because there are two level of threads. So user level multi-threading and kernel level multi-threading. So both are available, and it depends upon you, like how you want to manage your application. So thread is a basic unit of CPU utilization. Each thread would have a thread ID, program counter, register set, and stack. So if you remember and recall, a process would have register set, program counter, its ID. Along with that, it has basically code section, data section, operating resources, open file, and signals. But in case of threads, thread would have this as its private part, and then this as a public part. So where each thread would be sharing the code section, data section, of operating system resources, and open list from the process which has created that particular thread. A traditional process is a single thread of control. So if we say what we have created a process, it means it's a single thread of control. So it creates only single thread. If a process has multiple threads, so it can perform more than one task at one time. So if it is on a multi-core hardware, so it means you have more than CPUs. Let me write again. More than one CPUs. Okay, so on a single. So now this is the differentiation between the single threaded process and multi-threaded process. So you can see code, data, and file section is common for the process. And because this is a single thread, so all the register and stack location would be used only by single thread. And then we have the code for multi-threaded. Each would have its own register and stack and ID. So this is basically 3 threads out of one process. So one process created 3 threads here. Some examples for this is a web browser is one example. Then you have word processor is another example. The third example is something like your web server. So let us suppose you created a website and it is getting popular day by day. Initially you have only 10 users or 10 users hitting your server. So hitting means like somebody opening your website. So let's suppose it's abc.ca. So there are 10 users. So you can create easily 10 processes for that. But let us suppose it become very popular and now you have 1 lakh user, what I say, 10,000 users hitting your website at the same time. Then what you need to do is to basically scale up your server. Now, what does it mean? You need to add in more RAM and computing power. So one thing is this. Now, because hardware, now you have one port over where your web server is providing the services. So multi-threading would actually help you to do this. You have 10,000 clients, those are hitting your server. So how your server would be managing? It would be impossible for your server to create 10,000 processes and then just revert back. Even then, if your server is creating a process, it has to give back the result back to the client. So it will be actually executing one process, returning back to the client, then listen to another request. In place of that, what is the concept is the server process is listening on the port, sort of mailbox, where your process is listening, means it is a location, a buffer where your processes keep on checking. Okay, so if there is new request, if there is new request, if there is new request. Okay, so when the server is listening to that from that particular port, a client basically send a request and put some content onto that particular mailbox. The server would read that mailbox and it will say, okay, this client number, any IP address at this port is asking for to open my abc.ca page. Okay, so what server would do? Server would take it to process it and return back the HTML page for the abc.ca. This is what it is doing. When you type in abc.ca, it hits the server of that particular website and then return back to you the HTML content for the first page. So this is how the process happens between client and server. Okay, so let us suppose 10,000 people, clients, are hitting the web server at same time. Now hitting the server means they are sending requests. So all 10,000 clients are requesting your first abc.ca HTML page. Okay, now how your server would handle? Number one, it can create independent processes for each and every request. So at same time, 10,000 processes, each would require some memory space and management. Then your server would certainly go down. It would stop responding. And if you would not like that website, whose server would actually get down. I remember that there are, like, I don't know how many of you are have an experience on working with web services or development of websites or web services. They might be knowing what I'm talking about. I'm saying is, whenever 10,000 clients are sending requests, it means you have to create 10,000 processes. Each process would take some space, and that could actually swamp your server, and your server stop responding to other clients. So if we leave this concept and come to the threaded part, what server would do? Server would listen to the client. Okay, there is a request from the client, and would create a new thread process. So it will run just one instruction and pass in the request content to the thread. okay, you have to run this function, each thread would actually run independently, and it would actually, now for 10,000 clients, it would create 10,000 threads. Now those threads would just be running in the space provided by the server, and then it would actually, each thread would be working as an independent. So each 10,000 threads would work and then come back to and return back the results to the client through this particular system. So basically this is the solution which is done and used by your web application. Okay, so one solution to have is server running a single process that accept the request, and when servers receive the request, it creates a separate process or thread, I'll say thread, to service this request. Okay, so each and every one process would actually create threads for the servicing, and each thread would be actually independently doing its services. So now let's see how many threads are actually running for each and every application you are running on your Ubuntu machine. If you remember, I told you about this location. We can go to any of the directory. So all these are the processes. Blue are the directories, and numbered are basically the processes. So let me go into 855. So I go in here. So I'm here into that particular folder, and then let me see if I can go into tasks. So I can see now this task folder for a one process is holding the number of threads this process is running. So how many are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 threads. A process number 855 is running right now, and there are other commands for this. So let me run through this. PS is one command to show you the running processes. Then it requires some attributes, and I'm using pipe for just visualizing the required content for one page. Now here you can see LWP is a lightweight process. This is the thread ID, and NLWP is the number of threads that process is running. So if we go on moving, you can see process ID 820 is running 4 threads. So the thread ID is 820, 837, 838, and 839. Similarly, if I go to thread number 855, you can see it is running 7 threads. So all these are the thread IDs here right now. Okay, the similar thing we can do by PS is another way of looking at it. So PS3 would actually tell you all the processes those are running here, and if I want to see the processes that a user is running, let us see the OCS. So I'm running these 2 processes only, and this is the hierarchy and the tree structure of it. Now I want to see the number of threads. So here is some command arguments, and here I want to see for the process 855, or I can just leave it to see whole processes. So everything is coming up here. So what is executed, which process is executing which thread, every information is floated here. So we verified this, that 855 is actually running 7 threads, and here we are. You can see this is our process ID, and then SSHD. Then I open this, and in that I'm running a bash shell process, and in that I actually executed this particular instruction. So this is our process which is running right now. There are 2 very good commands that I just want you to note down. One is top. Top is basically giving you the utilization. It's something similar to your window task window task application for Windows. So you can see the utilization of CPU, and the process ID, which actually takes your computation, how much computation it is using. So whole of information is coming here. Then there is another command that is htop, which is more like more refined. It could actually show you the hierarchy and the tree. So basically this is just showing all that information as tree structure, like which program is running and where it is running, how much information it is basically taking. So from exiting from these programs, you have to press Q. So most of the programs which you are running for terminal, like top, htop, And let me see if I have Glance also. Oh, sorry. Okay, so it's not installed yet. We can install this as a Python based. There are more functionality to it. You can always see. These can always also show your threads and the processes. So whenever you develop an application, you want to see, debug, and get the information about that application you are developing. You can always look at the processes, its utilization, and also the memory size, memory footprint, how much actually memory it takes. So I was working on one of the project for IoT based. So we wanted to know about the footprint of the software that we are actually running onto the Raspberry Pi. And we use some steps here. Even there are commands to get the information back into the program. So based on that, we were actually taking some steps to correct a particular application or set right the parameters. So this is very basic, and you can use it for your understanding and knowledge and looking at what processes are running. So press Q, you will get out of this particular thing. So from proc, you can always look at other features of the process also. So I told you that the information is already available. I shared this set of instructions for PS and other into lecture 3 on my learning space, so you can find out this markdown page. Okay, so moving forward is so what are the benefits for threads? So basically it creates the responsiveness, may allow continued execution if the some part of it is blocked. Let us suppose you have 3 threads, one is blocked due to IO, others would continue to work because they are independently working. And certainly there may be some sharing of information that can halt your one of the threads for running, but because there are multiple threads those are running, so it is always good. Remember, you should not create infinity threads. It depends upon how much memory you can actually use it. Okay, then the resource sharing. So the resource sharing is easy. Threads share the resources of process easier than sharing and memory message passing, because already the information is being shared by the memory chunk is already available, so they can share the information between each other very fairly easily than creating a separate region for shared memory as we do in the processes. So it's super easy for uh, threads. Now it's also economical because context switching, process creation has a lower overhead. This is what is whenever a process has to be created, it has a different PCB, where we have to look at and allocate more memory space for each and every process. But in case of thread, it's basically sharing all the resources, so it's also economical and performing context switching because the information is less and most of the information is also shared by the thread, so it is also easy for performing thread switching as compared to context switching. So context switching is happening for your processes. Scalability is also one of the main concern when we talk about anything, whether it is hardware or your application. So whenever you develop your web server, coming back to my web server, your first thing that you would be thinking over is what is the user base, how many user, number of users, what is the user base, how many hits you expect. Based on that, you can start with something smaller. So you can start with something 8 gigs of RAM processor and 8 gigs of RAM and 4 core processor, so you can serve the fairly good amount of users. And as you are keep getting 10,000 hits per day or per hour, then you need to actually think over to increase your server or to change your server. So for that, you have to increase your RAM to let us suppose you want to make it 32 gigs and you want to move on to 16 core processor. So there are different requirements. So this particular thing is called scale up. This is called scale up because we are scaling and adding hardware and replacing the old one. This is called scale up. Okay, now in case of Hadoop, if I talk about Hadoop, it actually add in commodity hardware together. So these are your machines. So it may be of 2 gig, it may be of 4 gig, it may be of 8 gigs, it may be of 2 gigs. So you are adding the small PC. So PC1, PC2, PC3, and PC4. One of the machine with better RAM would be taken as master and all others would be client, and they would be sharing information through network. In Hadoop, the architecture is scale up. Let us suppose your application requires more computation power. So what you do is you add in more machines to your network. Okay, so you just add 8 gigs of RAM, 2 machines, and you are not replacing anything. And this architecture is called scale out architecture. Each and every application you develop, you need to take care about the scalability, and the same concept would also be happening here. If I talk about threads, they provide you a functionality of scalability. You can create more threads from the same application if your hardware is supporting more number of, it has more number of cores. Let us suppose you can create 4 threads if it has 4 cores. You can create 16 threads if it has 16 cores. So based on that, you can scale up your application based on the hardware. So this process we will be discussing further, but I hope I'm able to tell what is the scalability, because it depends upon the number of processes you are actually running. Okay, now multi-core programming. So in multi-core programming, we have, again, that's what I was talking about. So this is basically dependent upon this. So whenever we have multi-threaded, we need to write down multi-threaded application based on a multi-core environment. Now earlier you had only single core processor, now you have multi-core. So there would be, you need to, as a developer, you need to write a new application which can create threads from a process, because threads are independent, they can work better, they can run in parallel. So that's why threads are always better, and that for that you have to rewrite your application that is, multi-threaded application. But it has a challenge, like to divide activities. So if you have application, let us suppose you have a LOC equals to 2000. Okay, so let us suppose this much is a bigger software. So if you have this much, then you have to divide these activities. Or let us suppose you have 10 modules. I talk like this. Okay, so if you have 10 modules, then you have to basically think over how many threads you can create, and those threads would also be in a way that it divides the whole task. So it should not be like you are creating 3 threads. One thread is doing 60% of the job, thread 2 is doing 25% of the job, and rest is done by this particular application. So that is also not acceptable. So you need to actually, that it actually divides the activities and also create a balance between the application or the threads work. Now splitting the task into your the thread, it also requires proficiency. So do you think that every program let us take an example, like if you have to write a program that read and count a number of words from a particular PDF file, can you write a multi-threaded application for this? So basically you can write down because that would be a concept that we are going to discuss next. So data splitting, there are normally, when we talk about a program, there are few things which is called serial code, which you cannot parallelize, and there are some chunks and the things that we can actually divide. Not whole program can be divided. It cannot, the whole program cannot be divided. So there are few steps that has to be serially performed. Like there are few steps for the parent to be done before it actually split the task into the threads or for the threads. So something is serial code in your program. Let us suppose you have 25% of the lines are just serial code, you cannot divide. Now pending 75% of the code you can actually serialize, parallelize. So for this 75 of work, you have to actually create threads which are balanced and which can actually share and divide the activities. Okay, now we have also need to look at the data dependency. So that data dependency would also create a problem. Like one process has to, let us suppose this is the dependency graph. This is the dependency graph here. So whatever T1 is actually executing, it has to go to the next thread. Okay, so let us suppose T1 is doing some computation, and then T2 would be actually, doing the computation, and then T3 would be doing its computation only after T1 is completed. So this dependency is also there. So that could actually create a problem when you are, creating multi-threaded problems. Do you think that a Fibonacci series we can create it as a multi-threaded application? We can create, but initial value to be, we have to manage it. Like how you code that. Now it's your task to actually write a code that how you would be actually splitting your task and data into different sections. You could do it. Everything is possible, but there would be dependency. So the dependency would actually be a bottleneck for the parallelism of your application or the job, because there is something has to be done in serially, then some data has to be passed from one thread to another thread so that it can start computation on other part. So some part it can run independently, some information it has to be shared or taken from other processes. So everything can be done, but still this is a bottleneck for writing a pure parallel task, because the code is always having some dependency on the parent or other processes. Now testing and debugging would be, I think, would also be a challenge for your threading. Parallelism, where we can run the jobs parallelly, and concurrency is where we have, more than one task, and they are trying to mimic parallelism, but they are not running in parallel. So concurrency is something like that. So it's just it try to mimic parallel behavior, but it's not actually running in parallel. It's just running sequentially. So that impact is actually called concurrency. Now there are two types of parallelism that can be performed: the data parallelism and the task parallelism. Now data parallelism is one example that I took. Is I have, let us suppose, 1 million PDF files, and I want to create dictionary out of it. So I want to create a dictionary out of it. Do you think that this task could be a data parallel problem? Can I divide this data into number of processors, CPU 1, CPU 2? Do you think that this is a data parallelism problem? I have 1 million PDF file and I want to create the dictionary. I mean, I want to extract the unique words from each and every PDF file. Okay, so normally whenever we do NLP based tasks, so we have huge set of data, and from there we extract those words, and based on that words we create a dictionary. Okay, this is the known knowledge, and based on that we make some prediction or recommendation. So this task can be one example of data parallelism, because we can divide the data and we can assign the different data into different processors. Each would be running same instruction. So the program is going to be same for each and every processor, whereas the data is going to be different for each and every processor. So that becomes the data parallelism problem, where we can easily just give a different chunk of data to work on for different process. So basically task parallelism is, let us take an example, like we all are sitting in a room. Okay, so I want you to create a program that basically find out three things. So when two things, let us suppose temperature and pressure in your, or humidity, three things: pressure, temperature, and humidity in your room. So now what would be the data for you? So let us suppose we choose 100 points in your room, and we are calculating these all three things. Now the task parallelism would be I assign one function. One function is basically one processor is just doing calculating the humidity. The other process is just measuring temperature based on the sensor, and other one is just measuring the humidity or the pressure. So basically, all three functions are assigned to different processors, but they are working on same kind of data. The data is same for each and every, the same sensor are feeding the data to those functions, but they are calculating different parameters out of it. Okay, so that's basically is a task parallelism. So when we have a task parallelism, each thread performing a unique operation. We will see and do that example today, where one is just finding maximum, other is finding minimum, and other is finding the average of the input string. We have data parallelism. So here is basically Hadoop is coming. So Hadoop works on data parallelism. So because a huge data is being generated, so the whole concept of Hadoop architecture is based on data parallelism, and it says data is more as compared to the instructions. So all the machines, those are connected under Hadoop system. Instructions are moved from the master to each and every node, where each node would be actually working on their required data set and performing the same kind of instruction. Sorry, I took you little out of operating system, but this is how we actually connect to the modern era of computing or PAL operating system. So these are the concepts which are basically are evolving and are used. If you remember, I also discussed with you Flynn's taxonomy. Flynn's taxonomy is given by SISD, SIMD, MISD, and MIMD. You need not to remember it, but S means single, M means multi, I means instruction, D means data. So single instruction, single data, single instruction, multiple data, multiple instruction, single data, and multiple instruction, multiple data. So these are the hardware architectures. Those are used for running different kind of set of instructions or the program. So all are coupled together to just make it simplify and bringing you back to what we were discussing. Thread is a unit of CPU utilization. We create threads from the process. Each thread does or do a set of tasks which is assigned to it, and then give back the return. Now each thread could be doing data parallelism, or it could be doing task parallelism. So either the same instruction is given to each and every thread, but the data set is given differently, or the same data set is given to each and every thread, but the operation to be performed on that particular part of data is different. So basically concurrent execution is, we have single core and we have multiple tasks. So multiple tasks are running. T1 runs first, T2 runs second, third, fourth, then again T1, T2, T3, T4. Multitasking is because each task is assigned for some time. Time slice is given to each and every task. So that's why they are running like this. First T1, T2, T3, T4, and then again. So each basically process is sharing some time, time slice of CPU. Now time slice of CPU means CPU is running continuously 100%, and we are allocating, okay, from 1 minute, if CPU runs for 1 minute, we have 10 tasks, we give, we have 6 tasks, we give 10 seconds to each and every task. If we have 6 tasks and your CPU is running for 1 minute, then we give, time like that. So basically that's time sharing. Okay, where there is more complexity to it when we talk about real-time operating system. So it's not always the time slicing. There are many other algorithms those can perform and do the things. So if you remember, we discussed about short-term scheduler, long-term scheduler, and mid-term scheduler. So all these scheduling are there. We will be discussing more on it on next chapter about scheduling. Okay, now parallelism. Here you could see that the task 1 is assigned to core 1. It is running there on time slice manner. Task T2 is running in a time slice manner on core 2. Now task 1 and task 2 both are running basically both are running at same time, and they are in time space, they are running at same time. So that's why they are running parallelly. Here in concurrency, nothing is running parallelly. They are just switching, context switching. So this is the major difference between parallelism or concurrency. Okay. Midterm scheduler is basically coming back to your question, Shao. Midterm scheduler is, let us suppose your whole of the memory is already, taken away by the processes, and all are in ready queue. Now there is no the operating system wants to use some of the RAM. Then what it does is it put back process from the main memory back to the disk. The processes which are running, those we bring into, or the operating system bring into the main memory. From the main memory, it goes to the higher level of memories, like onto the CPU. Okay, so the process is loaded into the main memory. From the loaded memory, it goes to the CPU. If operating system suppose, okay, this process is taking, larger memory, or it requires itself some RAM, then it will put back some of the processes back to the disk and then bring them again whenever it is required. So that task is actually done by your midterm. So coming to how much parallelism we can get, how much speed up we can get by dividing your task into smaller threads. If we say, okay, I have 10 cores, I divide my process into 10 different parts, then I'll get my process would run 10 times faster. Do you think, is it true? Like if I have 10 cores and I have 1 core, okay, so the same application A is running on both. Do you think that if I designed A for this with 1 thread, and if I design this for 10 cores with 10 threads, would they be, the computation time here would be 10 times lesser than here? Exactly not 10 times faster, but it would be somewhere in between. So there are some laws for it, how much, parallelism you can attain. And it's not about, adding keep on adding multi-core system. It does not mean that you are going to add more parallelism. There is always a bottleneck. If I talk about, people management, if I'm developing a software, I need 5 developers for my task. Okay, so if I think of, if I add more 5 people to my team, would that be the time of development would be halved or not? Not, because there are always more communication between the team. That takes more time, and that actually makes my development slower than 2x, but obviously it will increase, but not that way. So something similar is also happening inside your machine. If you keep on adding more multi-core system, it does not mean that you are going to take, if you added n cores, so it does not mean nx you are getting. So this is the law for that. So Amdahl's law is one, which says if you have a program, it has S serial portion and N processing cores, then the speed up that you can gain is 1 over S plus 1 minus S over N. So this is the speed up you can gain. Let us suppose, for example, if you have 75% is a parallel code and 25 is serial, how much you can get how much time or like speed up would get, it will be adding 2 cores it will gain a speed up factor of 1.6 times. So if you have one core, it will take one unit of time. Okay, so if you have two cores, it will be divided by 1/6. So the speed up factor would be 1.6 here. So if n approaches infinity, like we keep on adding n number of cores, what would be the speed up factor? This would be equal to this 1/s. So it depends upon how much serial code you have in your program. Based on that, you can take you have to write down, you have to create a structure or data structure. In that way you can actually split your task easy way, but there is always some serial code. So as we keep on increases n, your speed up factor would become only 1/s. Okay, so if we keep on adding the n is infinity for this, how much would be the max speed up would be 1/2.4, so it is equal to 4 times we can actually do. So serial portion of application has a disproportionate effect on performance gain by adding additional code. This, however, Amdahl's law does not take into new multi-core system. So this is here, it is just adding more distributed system. So there is new formula for it. If we don't want this to be calculated, but a new formula for it to calculate how much speed up factor we will be getting. Now coming to the threads back, there are two types of thread, user thread and kernel thread. User thread is created by user application and managed at user level, whereas there are different thread libraries that we can use. We will be working on pthreads, and then we have kernel threads, so which are supported by your kernel, and all the operating systems are basically giving or powering that particular support for those threads. In multi-threaded models, we have different models for it, many to one. So many user level threads would create only one kernel threads, because actual work has to be done by kernel. So many user level threads can create one kernel level thread. So if one thread is blocking, it will block all other threads. So it is not suitable for multi-core system, because only one thread is working at one time. So there were like systems which were using only many to one threading, multi-threading concept. Then we have one-to-one multi-threading concept, where each user level thread can create a separate kernel level thread. So if you are creating thousands of user level thread, your application can create 1,000 user level threads. It is going to create a 1,000 kernel level threads. So the problem is that it is going to be it is going to overhead your operating system, because there are so many threads those have been created by your application. But mostly you would see that this mechanism is used by your Windows, Linux, and Solaris systems. Then we have many to many. In many to many threads, one thread can create many user level threads are mapped to many kernel threads. So it may be possible that one is mapped to many, and this mechanism is basically provided by, if you remember, by the interface or runtime environment. So that basically creates this interaction. So it allows the operating system to create a sufficient number of kernels for a user thread. And now is a two-level model. So in two-level model is more flexible. It says, okay, the same number of user level threads would be created by your the operating system based on the hardware. Let us suppose it is a four core hardware. Now your operating system can create at max one for one particular thread. It can create four kernel threads for one kernel for one user level thread. It can create four kernel threads. If the same application is running on 8-core processor, so it is flexible, and it can create 8 threads for the same user thread which was earlier on a different machine. So it basically allows the portability also, because many level of threads could be mapped to many different levels of kernel threads based on the hardware which over which it is running. Okay, now moving next is threaded library. So threaded library, we are going to discuss pthreads. So and POSIX pthreads we are going to use and see how we are creating those threads. Then there are two types of threadings. One is asynchronous threading and other is synchronous threading. In asynchronous threading, once the parent creates a child, it continues to execute itself, and then the child can actually execute concurrently or independent of each other. Whereas in synchronous threading, the parent thread creates one or more children, and it must wait for its children to terminate before it resumes the execution. So there are two types of approaches that can be used. And now let's quickly move because time is about to end. Just quickly see some examples. Okay, so this program is basically used for creating one thread. So if you see here, for creating threads in your program, you have to use a library, this pthread.h. Okay, so this header file you have to use, and another function which is to be used by your thread would needs to be declared, because each thread would be working on a different function or the piece of the code. So here this is for initiating one process. Pthread is for initiating the user, the thread. This is for holding the attributes we are not touching right now. So you are aware about this instruction. If PID is equals to 0, it means it's a child process. Now child process creates a pthread. This basically initiates the attributes taken from some variable attribute, and then this command would actually create a thread. So here is pthread underscore create. This is the ID or the pointer to that particular thread which will be created. Then we will discuss attributes in your next chapter. So what attributes can be passed here? Then this is the name of the function which the thread would be executing. Okay, so we are just passing this information to it, and here if we want to pass in some arguments to the function, that we will see we are not passing any arguments. Once the process is the thread is created, it would start running. This instruction would create one thread and it will start running. Your child process, this is child process. So this child process would wait using this instruction. You remember the wait here is waiting for the child process to terminate. This instruction is waiting for the thread to terminate. Okay, so pthread underscore join will wait for this thread to actually terminate when it actually perform its execution. Once it is done, it will print the value of child has already held this value. Okay, then else is if the PID is greater than, so this will execute, and at this it is waiting for the process to run or the child process to terminate, and it will actually print the value for this. So this is something which is there for creation of the threads. Now quickly we can look at another example. Queue. So I go out of it, and now let's look at this program. Here is we are passing some arguments here, and those arguments are basically taken by your process. So if you can look here, we are not creating any child process for this particular program. We are rather just creating a thread that would perform some work onto the arguments those are passed. So if you can look here, this we have passed some attributes. Those are scheduling attributes, and then here we are creating that particular thread. So one thread would be created here. This is the pointer to that thread, then arguments, and then runner is the function that this thread would be running, and these are the arguments which are passed to the main function. So we are just passing that, and based on this main process, this will create a thread and it will start running. Runner is this function, so it keeps on adding the value. So it's basically performing the summation of some value which is passed. Okay, and then it would be just waiting for the process would wait for the thread to terminate, and then it would actually perform printf the sum which is returned by your what I say is basically they are sharing this these variables, so they are sharing, so it's basically just taking that value. So here you can see there's no sharing of our data, it's just taking that variable as is and just printing that. Once the thread terminates, it just print that value. So this part is run by the parent process, and these are the threads they are doing. Let me just go to the third example, and then we run one example, and that would actually give you some idea on it. What has been done here? Now this example we will be doing. So I created some variables, and there are three functions. Those functions are calculating, average, maximum, and minimum. We start with the main function. We are passing some arguments. We are structs for the threads. There are three structs we have defined. We allocate the list, and for each thread we are creating those threads. So this is pthread underscore create would create thread 1, and then it would be running. We are not passing nothing as an attribute to this thread. So calculating the average, this is the name of the function, and then we are passing and the number of arguments. So number of argument is here, so we have already taken. Now here it will create another thread, and to this thread we are passing calculate maximum function, the same number of argument. Number 3 thread id or the pointer to that, then calculate minimum. So this is another function, so the same number of arguments we are using. Those threads would be created. Your parent process would be waiting for thread 1, thread 2, thread 3. So it will wait for all these threads to terminate, and thereafter it will actually print the average, the maximum, and the minimum. So those are basically coming from different threads. So now you can see after main, we have created three functions. One is calculate average, which actually performed and would be executed by thread 1, maximum thread 2, and then the minimum is by thread 3. So thread exit 0 is basically terminating the thread. This will actually terminate the thread. So let's go out and do gcc thread 3.c. Now remember, here we need to give in the library that is pthread. So we need to give the extra flag here. So this would be done. It will run. Now we can see it is already executed. So here I have to give the list that I want to find out the sum of. So you can see I pass in the list of the arguments, and this actually returned me the average, maximum, and minimum. So all this is done by different threads. So what we do is we created a main process, and within that main process we created three threads. Those are running.